Good afternoon, everyone. So here there is my next lecture based on lasers, and the subject is optical communication. We have already discussed with lecture 1 and 2 with types of fibers, with types of modes in the particular fiber. So here we are going to now see what are the different sources used in optical communication with fibers, and in that category we have one source which is called as lasers. The other source is LED. So lasers has an acronym that is light amplification, stimulated emission, radiation. So we will see how these lasers will work in and compatible with optical fibers, and what are the characteristics, what are the main requirement to build a laser. So now we can see from this slide that laser is an acronym for light amplification by stimulated emission of radiation. Laser, we already know that has a coherent light. It has the photon which is emitted through laser is having same phase, same frequency and same state of polarization. It has a narrower beam width as compared to LED. So lasers can produce high optical output power. In fiber optic communication application, we require these high optical output power. So semiconductor lasers have powers in milliwatts, which is around 20 milliwatts, which are available in market. So as laser is coherent, a high percentage, that is 50 to 80%, can be coupled into the fiber core. So this is the basic definition for laser. What are lasers? What are the basic characteristics of laser? It has a coherent beam, it has a narrow bandwidth. A laser can produce a power which is very much higher as compared to LED. LEDs have power in microwatts. On the other hand, lasers have power in milliwatts. So obviously laser have much higher power as compared to LEDs. So we can see the basic operation of the laser. So with this basic operation, we have three fundamental operation of the lasers. First one is the absorption. The second one is the spontaneous emission, and the third one is the stimulated emission. So for absorption is a phenomena. Suppose we have two energy levels, but one is the ground energy level and the other one is the high energy level. We have E0 and E1. So in the absorption, the number of electrons in E0 is much higher as compared to number of electrons in the high energy state. So absorption is the phenomena through which we can incident a photon on the electrons at the bottom or at the lower energy level. When this photon hits this particular electron in the lower energy level, it will move towards the high energy level. So we will see here the difference of the energies between two levels is h nu. With the help of Einstein relation, you can easily compare that E is equivalent to h nu. So with this Einstein relation, we have in terms of E, we have the difference between the two energy levels, which is E1 minus E0, and it is equivalent to h nu. So after the absorption, the electrons reside on the high energy state, that is E1, and for a certain period of time, that is called as lifetime or carrier lifetime, the electrons will reside here only. After that, we have two processes involved, which is called as emission process. The first one is the spontaneous emission process, and the second one is the stimulated emission process. As the word signify itself, that is spontaneous emission, the electrons will move spontaneously from high energy state to lower energy state. We do not require any external energy or external power to make it from falling from upper energy state to high energy state. So here we have simply the electrons will move towards lower energy state. With this second diagram, you can see that the electrons will move to the lower energy state E0, and there is a release of photon which is having a same energy. That is the difference between the two energy levels, that is E1 and E0. So we have a free photon or the release of photon which is having a energy, that is E1 minus E0. In the case of stimulated emission, we have to incident a photon here firstly on the upper energy state atom, and then the atom will fall down into the lower energy state. So in this process, once you incident a photon in the higher energy state residing atom, then there will be release of two photons. So with one photon, we have two photons. So it has more energy as compared to spontaneous emission. So these processes are, we can see here in later on how these processes can be involved in the basic operations of the lasers. So in if we talk about LEDs, that is light emitting diodes. So if you talk about light emitting diodes, it has two processes involved, that is absorption and spontaneous emission. Obviously, the LED doesn't have the coherent beam as lasers, but it is also optical source. It can be compatible with fibers. Usually, LEDs are compatible with multi-mode fibers. As the multi-mode fiber diameter is much higher as compared to single-mode fiber, we can use LEDs with multi-mode fiber. So, in the case of LED, we have absorption and spontaneous emission. But for lasers, we require much more population in the high energy state, and we incident one photon on the high energy state residing atom, and then it will fall back down to the lower energy state, releasing two more photons. So there is a chain of or a gain process involved in the process of stimulated emission. As there is absorption, there is a process called pumping. So obviously once you incident a photon on making the electron to move from lower energy to high energy state, there is a process which is called as pumping, and this process make the population inverted in the case of absorption. So earlier the population of atoms in lower energy state is higher. After the pumping, we can see that the population at the high energy state is much higher as compared to lower energy state. So what are the conditions for large stimulated emission? So we can see from these figures, in the first figures, all three processes occur together with a balance between absorption and emission. So in the first figure, we have electrons and holes. So in the lower energy state, we have earlier electrons, and in the upper energy state, we have holes. So we can see from this figure, lower energy state consists of only electrons, and the high energy state consists of only holes. But once we do the pumping or absorption phenomena, lower energy state atoms will move towards high energy state, and there will be also creation of holes. So in this case, we can see that two conditions to be satisfied for stimulated emission to overcome the spontaneous emission. That is, the first required condition is the population. The population of the excited level should be greater than that at the lower energy level, and the radiation density in the medium should be very large. So this is the main requirement for the lasing action to be occur. So there is a word which is called as population inversion. We will see in the later slide how this population inversion will work, and how this is going to be useful for stimulated emission. So now we can see with this diagram, that is population inversion. So initially we have absorption, then we have two phenomena like spontaneous emission or stimulated emission. So in the population inversion, lower energy state atoms are much higher as compared to high energy state. We can draw a diagram for this. This is density of atoms, and this is energy level. So we have initially, the curve is like this, exponentially decaying curve. So initially E1 state have higher density of atoms as compared to number of atoms in the high energy state. This is before population inversion. But after population inversion, the scenario will change, and there will be a difference. That is, at E1 we have lesser number of atoms, and at E2 we have higher number of atoms. Same, the x's are energy level, and this is density of atoms. By this graph, you can easily see the number of atoms in lower energy state is N1 initially. The number of atoms in high energy state E2 is N2. Obviously, here N1 is greater than N2. But when the population inversion will occur, after that, what will happen? The lower energy state is N1, which is very much less as compared to N2. So we require this phenomena to have stimulated emission in the case of the lasers. So with this diagram, we have only shown this, that what is absorption, how the absorption will occur, and then spontaneous and stimulated emission. Obviously, there is one photon release in the case of spontaneous emission, but in the case of stimulated emission, there will be two photons released. So this is the normal state with population density N1, and excited state with population density N2. We can see these three phenomena occurring in simultaneously. So what is population inversion? At thermal equilibrium, photon absorption and emission process takes place side by side, but because N1 is greater than N2, so absorption dominate. Lasers operation require stimulated emission exclusively. We already discussed this. And to achieve this, majority of atoms should be at high energy level than at lower energy level. So energy to be supplied to the laser medium to raise the atoms for the lower energy level to high energy level, that is excited level. The process by which atoms are raised from lower level to higher upper level is called pumping. So this process is very much important, that is called as pumping. Now we can see in the next slide that in stimulated emission, incident and stimulated photons will have identical energy, identical wavelength and line width. That is why it is called as coherent. So it has identical, the photons which are released through stimulated emission having identical energy, identical wavelength. Narrow line width, obviously the lasers have narrow line width, identical direction, identical state of polarization, identical phase, coherence and state of identical polarization. So coherent means also same phase, frequency, state of polarization, etc. So now we have a basic laser structure which is called as Fabry-Perot lasers. So in this structure we have two mirrors. One mirror is this side, second mirror is this side. Both the mirrors have reflectivities R1 and R2 and the mirror distance is capital L. So we have a phenomena here, that is the laser amplification. The laser amplification will help only in this cavity. So homojunction device with cleaved ends demand for high threshold current which is greater than 10 to the power 4 ampere per centimeter square due to lack of carrier confinement, hence inefficient light source. So we will use this kind of arrangement to make it happen. There will be much light as compared to LED. So what will happen here? We have to see the coherence length or the length between the two mirrors which is equivalent to half of the wavelength, that is lambda by 2. And integer multiple, that is q by n. So there is a formula for calculating the length between the two mirrors, that is L is equivalent to lambda by 2 multiplied by q by n, where lambda is the emission wavelength of the laser, q is the number of modes or the integer values. Q is equivalent to number of modes. Longitudinal modes we are having in this structure, and small n is the refractive index of the medium. So with this formula we can calculate the proper length of the two mirrors, that length between the two mirrors, so that there will be laser amplification. So this is a necessary condition for laser amplification or laser oscillation. So these mirrors are basically, first mirror is 100% reflective mirror and the second mirror is partially reflective, that is less than 100%. So here in this diagram we have seen that because lasers and LEDs are made up of third and fifth group element alloys, so it is made up of P type of gallium arsenide and N type of gallium arsenide, and in this between there is an active region. So the electron hole and hole recombine in this particular region in this structure, and then there will be emission of light. So the emission of light is through this proper active region which is in the form of photon h nu. So this particular active region is called as Fabry-Perot cavity here. So with this Fabry-Perot cavity we can calculate many things, that is L is equivalent to, we know, lambda by 2 multiplied by q by n. Also we can find out F, which is C upon QC upon 2NL. If you put lambda is equivalent to C by F, you can calculate the value of F, that is the frequencies in the Fabry-Perot resonator. Also we can calculate delta F. Delta F is basically F2 minus F1. So we can calculate the value of F2, that is C by 2 NL, that is 2C by 2 NL, because for F2 we will put Q is equivalent to 2 and for F1 Q is equivalent to 1 minus C upon 2 NL. So we have easily delta F value which is C upon 2 NL. So this is the proper spacing between the two modes in the laser. So we have this type of gain curve and the spacing between the lasers are like this. So this is spacing, or you can see that this particular spacing, this is F, this is spacing is delta F which is C upon 2NL. This is particularly gain curve which will fall on this spacing, and we will have these kind of modes. So laser output spectrum, we can see here, that is the mode separation that is given by lambda, delta lambda or delta f, delta lambda or delta f. So these longitudinal modes are existing in this gain curve, and we have a single mode operation laser like this. In the next figure we have shown, that is, this is the single frequency laser which is having less than 0.04 nanometer line width. So it has a very narrower line width as compared to LEDs. So we can easily compatible these lasers, these kind of lasers, with single mode fibers. So these lasers can be compatible with single mode fibers, and these lasers are single mode operation laser. Next we have heterojunction structure. So this is a new structure which is called as heterojunction. So improved carrier confinement, thus lower current densities here, that is around 10 to the power 3 ampere per centimeter square. Stripe geometry is another kind of structure. So with this stripe geometry, you can see that it has a p type of p plus gallium arsenide, n plus gallium arsenide. In between that, p aluminium gallium arsenide, n aluminium gallium arsenide, and there is a stripe of active region. So here it is stripe of active region. So it is similar to PN junction, but we have a depletion region which is called as, in the PN junction is called as, here is, it is active region. So next is the broad area double heterojunction laser. So broad area has an advantage over stripe geometry. In stripe geometry, the laser light will be from the whole stripe, but in broad area we have the light from the broad area. So it is also not so good as compared to stripe geometry. So we can have moved to DH stripe contact laser. You can see that is DH stripe contact laser have a similar structure like stripe geometry structure, but in this we have a particular section which is through which the light is only externally outcome from this point. So we have a proper narrower light as compared to the broad area which we have already seen. So in the broad area, the light is lost, the loss of the light is much wider as compared to this particular DH stripe contact laser. So to overcome broad emission problems while reducing the required threshold currents, a laser structure in which active region does not extend to the edges of the device were developed. So in this structure, the major current flow through the device, and hence the active region is within the stripe. Generally, the stripe is formed by creation of high resistance area on either side by techniques such as photon bombardment or oxide isolation. The stripe therefore acts as a guiding mechanism which overcomes the major problem of the broad area device. So this is the basically it's the same thing, that is the Fabry-Perot resonator. So there is a temperature dependence of the oscillation wavelength in the laser. So the refractive index of the material of DFB laser, that is distributed fiber Bragg grating lasers. So these have anti-reflection coated on both the sides, and with this we can easily form our lasers. So you can see with the figure, we can easily see that in distributed Bragg reflector, that is DBR laser, we have a corrugated region outside the active region. So there will be a photon will fall on the corrugated region, and the photon will come back and forth, and that's why the gain or the intensity of light, you can say intensity of light is much higher. So these type of arrangements we can use to make a laser much more intense or much more having producing light as compared to the basic lasers. So basic lasers, we have semiconductor injection laser, double heterojunction, stripe geometry lasers, but distributed Bragg reflector and distributed will give you the much more proper or efficient light as compared to the basic lasers. So this is a new form of laser which is called quantum well lasers. It has a well type of structure. The P and N will be made up of P indium phosphide and N indium phosphide. These all materials are direct recombination materials. When light is confined into a cavity, smaller its wavelength, it behaves as a particle, that is quantum, rather than as a wave. So most semiconductor lasers are very thin, that is around 20 microns or so. So this vertical direction, but this is not the thin enough to cause quantum behavior. So in quantum wave laser, the confinement factor is much more higher as compared to the earlier lasers, because it has a well type of structure. The light will be confined in the wells and they will produce much more higher light as compared to basic semiconductor injection laser. So these are different forms of laser which we can use to overcome the problems in the basic lasers. So quantum well lasers have a much reduced sensitivity to temperature change. So with that change in the temperature, there will be no change in the quantum well lasers output as compared to DBR or DFB, distributed fiber Bragg grating or distributed Bragg reflector. The quantum well lasers structure provides only one line which has a narrower line width. Then for non-quantum well structures, the wavelength of the light emitted by quantum well is determined by the width of the active region rather than just the band gap of the material. This is an important point. So lasers with a single active region are called single quantum well lasers, and number of quantum wells are used on the top of the ether to build a multiple quantum well structure. So we have already seen this, that is multiple layers will be provided to make it more intense, or more light will be provided through these lasers. So a disadvantage is that multiple quantum well laser produces a broader line width than single quantum well laser, but still narrower than comparable to all other different basic laser structures. So now we have laser characteristics. So full width, half maximum peak wavelength, line width, threshold current, operating current, rise time, output power, operating temperature. These are some parameters through which we can characterize our lasers. So optical output versus drive current of a laser is drawn here. Here we have a optical output power, PI characteristic. So after a certain current, there will be no change in the power, but after some time, that is the threshold current, there will be a change in the power. We can calculate the value of the slope, that is dP and di, through which we can easily find out the external efficiency which is dependent on this slope dP and di. This is the next graph which is based on the temperature. So as the temperature changes, there will be a change in the optical power. There will be a dependence of optical power on the temperature. As you change the current, there will be a change in power also, and after changing your temperature, there will be a change in power also. So we have at 20 degrees Celsius this curve, 35 degrees Celsius this curve, then 50 degrees Celsius, then 65 degrees Celsius. We have different temperature ranges, and for these temperature ranges we have optical powers. So you can see that higher the temperature, the optical power is constant. So there will be no change in the power as compared to LEDs, which has a much more dependence on the temperature as lasers. So thank you so much. This is all about the optical sources. There is a wide area for these lasers. We can explain much more about it. In short, I have selected some topics so that you can have a crutch of these topics, and you can easily go through all the details of the lasers. Thank you so much.